Oh, man, if you thought the last lesson was exponentially fun, get it? We're about to log some real fun time. That one was good. I'm going to keep that. I'm not even going to try and re-record it. That was great. So, anywho, we're getting to some graphing of some logs, but let's first jot down some properties of those exponential functions of yours. So we have an exponential function. It's f of x equals a to the x, where a is going to be a positive number greater than 0, and it's not equal to 1. Okay? Not equal to 1. Cool? So our domain of our exponential function, we're talking about like our parent function here, would be all real numbers, or we can go with negative infinity. Yeah, change marker there. Let's go with blue. There we go. Negative infinity to positive infinity. And then, let's see, our range. Our range, if we're looking at these graphs, there's an asymptote at y equals 0, which, will answer this part. So our range, it's never going to get there, right? It's always going to get infinitely closer as we go either further left or further right, depending on which graph we're looking at. So our range is going to be y is greater than 0, or we could write it as, I was almost going to do a bracket from 0 to positive infinity. However you want to write that. Up here in the domain, we can also say that x equals all real numbers. That's another option there of how to write that. And then our intercept. Here it's going to be crossing at 1. So 0, 1. I like it. Wonderful. Fantastic. Let's keep going. So let's get talking about some logarithmic functions with base a. So a will be some number, right? But a needs to be greater than 0 and not equal to 1, once again. So similar kind of thing going on as compared to exponentials, right? And it's denoted by y equals log base a of x, okay? And is defined by, or y equals log base a of x, if and only if x equals a to the y, right? We can write it in logarithmic or exponential form. And we're actually going to practice that here in just a little bit. The domain of a log function, actually, we're not going to get to that yet. Spoiler alert. Sorry, the domain would be that x is greater than 0. Okay? So here my domain is x is greater than 0. Up here, my range was y is greater than 0. Domain and range have switched, it appears. I wonder why. We'll get to it. The definition of a logarithm gives us the ability to write an equation two different ways, even though these two look different. They both have the same meaning there. All right, so let's practice with writing in the different forms. So converting the forms. Exponential to log form. Some of you may remember the loop and swoop. I'm a big fan of the loop and swoop just because it's fun to say. Let's go for it. Actually, I think I'm going to go down one marker size here. It seemed a little bit too heavy. All right. So my loop and swoop, I start with the base, swing around to the 9 and then to the 2. So I would have log base 3, start with the base, of 9 equals 2. All right, so there's my log form. Wonderful. Let's go down to the one with e to the x. So I would have log base e of 11 is equal to x. Log base e of 11 is equal to x. And some of you might be like, hey, wait, doesn't log base e have its own thing, right? Yes, it does. It's natural log of 11 equals x. So either one, this or this, okay? Either one of those would work, right? They're equivalent. Okay, so log base e is natural log. It's just so fancy, it's got its own one, Log base 2 of x equals 15, so we want to put this into exponential form now. Well, I'll start with the base. So 2 to the 15th is equal to x. 2 raised to the 15th power is equal to x. And here, it may help if you write it as log base e of 4 is equal to x. And then I would have e to the x is equal to 4. E to the x is equal to 4. Some of you might be able to just remember that, it's like a pattern, but it might help to write it out as log base e of 4 equals x. All right, I like to write it out like that because then I can see the consistency. Wonderful. I don't know why I didn't circle all these. Circling them is fun. Cool. Bingo, bango. We're moving on. So remember how we talked about how the domain and the range were switched in those two? It's because we know they're inverses of each other. Those x and y values switch on our graphs, right? We switch them when we're trying to write the equation. Let's do some of that right now. So first off, let's graph the exponential function f of x equals 2 to the x. And I'm going to do so with a handful of values. Let's see here. I'm going to go with a green marker. That sounds lovely. I'm going to go with -2, -1, 0, 1, and 2. And when I plug those in, when I put them in for x, I have 2 to the -2nd, which is 1/4. 2 to the -1st, which is 1/2. 2 to the 0, anything to the 0 power, remember, is 1. Which is why in the parent function of our exponential functions, we start always crossing at 1. It's because anything to the 0 power is 1. Once we start shifting up and down, left and right, that'll change things. But in our parent function, it's going to be 1. 2 to the first is 2, and then 2 to the second is 4. And you have had experience in graphing these back in Algebra 2 Honors. We're going to do a little more with it here in PCH, Pre-Calc Honors. All right, let's go ahead and plot those. And there we have it. And remember, there is that horizontal asymptote here at y equals 0. I'm gonna use my ruler there, and I'm gonna draw in that asymptote. Let's go with a lighter green for the asymptote, maybe. Lovely. There is my horizontal asymptote. All right. So we have our domain of this one. We know our domain is x equals all real numbers, or you could write it as -infinity to +infinity. Our range would be y is greater than 0, or you would do from 0, not including it, to +infinity. And as we said, our horizontal asymptote is y equals 0. Lovely. Now we want to find our inverse. So how do we go about finding our inverse? Well, as we said, we want to switch our x's and y's, so we're going to do that when trying to find our inverse as well. So I'm going to start with, instead of y equals 2 to the x, we're going to have x equals 2 to the y. That is a goofy looking 2 and equal sign. Let me try that again. That's a little better. All right, now I'm going to resolve it for y. Okay? So I kind of skipped over this first step. Change f of x to y, then switch x and y. Now we're going to solve for y. Well, how do I do that? Well, remember how we just did some of those problems with changing from exponential to log form? That's where this is useful. So I'm going to have log base 2. The base goes first, so base 2. And this time our loop is going back the other way. So log base 2 of x is equal to y. So there we go. We have f inverse of x would be log base 2 of x. Cool. There we go. Let's go ahead and plot this. Now, I find it easier when graphing to think in the exponential form than switch my x's and y's. Since I already have my exponential form here, I can just flip-flop. So I'm going to have 1/4, and I'm going to have, -2. I'm going to have 1/2, -1, and there we have it. All right, all nice and filled in. Our x's and y's switched. Again, whenever I'm trying to graph logs, I often think of the exponential and then reverse them. So the math is a little bit easier. It's easier to think 2 to the power, 2 to like what power, 2 to the second power gives me what, 2 to the third gives me what. It's easier to plug them in rather than thinking about it in a log. All right, let's graph it. So there we have it. We can toss an asymptote on there. I'll use a lighter purple color, plum in this case. And now my asymptote is going to be x equals. Beautiful. X equals 0. Since my x's and y's switch, so does my asymptote. And you're going to see that our domain and range also switch. My domain on this one, it starts at 0, not including it, and it goes to +infinity. So it's x is greater than 0, or from 0 to +infinity. And then for my range, I've got, it goes all the way down, all the way up, right? That's -infinity to infinity, or y equals all real numbers, or negative infinity to positive infinity. And then my asymptote is x equals 0. Everything flippity floppity. You will also, I want to point out with inverses, always remember that it reflects over this y equals x line, which is a 45, if the graph is correct. But it's gonna reflect over that y equals x line. It doesn't look like this one's scaled perfectly. Bummer. It's kind of way out of whack, but whatevs. It's gonna reflect, whoops, over that line. And you can see clearly that these do just that. They reflect over that y equals x, that parent function of our linear function. Cool. Wonderful. I think that's a good amount for that one. We can keep on moving, keep on grooving. Let's go. All right, now we got a little more fun here, it looks like. So we're going to do graph another exponential. We're going to find its inverse, which would be a log function, right? So let's start with the exponential here. We have y equals 3 to the x minus 1 plus 2. Whew. We're throwing some at you right away here. I like it. I'm a fan. I'm gonna go with the blue. We're gonna go blue, dark blue. All right, that way I can use light blue for my asymptote. What's the asymptote gonna be? We'll find out. Well, maybe you remember. I don't know. All right, let's do it. I like to pick my x values. Sometimes we'll say like some smart points. I like to have that negative 2 for my exponent, -1, 0, 1, 2 if possible, if it works out nicely. Here, I can do that. I'm going to throw in -1 for x, and then I'll go to 0, 1, 2, and 3. And when you think about it, x minus 1, that's a shift to the right 1. So if I normally would do -2, to the right would be -1, which is why I started there. Awesome. Fantastic. Lovely. So let's fill in our y values. If I plug -1 in, I'm going to have 3 to the -2nd, which is 1 over 9, right? So I'll have 2 and 1/9. I'm going to leave it as a mixed number there. Really doesn't matter that much in this one. If I plug in 0, I'm going to have 3 to the -1st. So that'd be 1/3 then, so I'd have 2 1/3. And then if I plug in 1, I'll have 3 to the 0, which is 1 plus 2 is 3. And then 2 would be 3 to the 1st, which is 3 plus 2 is 5. And then I'll have 3 to the 2nd with this one, which would be 9 plus 2 is 11. So now let's go ahead and plot these points. And boom, there we go. Yeah, one of those went off the graph a little bit there. All good. So I just get estimated. But with the 2 and 1/9, 2 and 1/3, it's kind of hard to get it that close. But remember, it's just above that 2 value. And when our asymptote was normally y equals 0, but according to transformations, we shifted this up too, our asymptote will do the same. I'm going to get my light blue with a ruler, give ourselves that horizontal asymptote of y equals 2 right there. Boom. Oop, a little too high. Like it. Awesome. So with our transformations, let's talk about that because we've referenced it a couple times. It went to the right 1 and up 2. Right? This is inside the exponential function. This is in the exponent, so that's a horizontal transformation. The plus 2 on the outside, that's an up and down, a vertical transformation. All right, our domain here, all real numbers, or negative infinity to positive infinity. I'm just going to write the 1. And then our range is going to be larger than 2. So we'll go from 2 to positive infinity. Wonderful. And my asymptote, I already said it, y equals 2. It's a horizontal asymptote. Lovely. Now part 2 here says find the inverse from number 1 and graph it on the same axis. I'm going to pick a different color. We'll go with red this time. And then let's find that inverse there. I'll do the work down here and then we'll jot it up there. So what do I do first? I switch my x and my y's. So I'm going to have x equals 3 to the y minus 1 plus 2. And now I want to resolve it for y. So subtract 2. And how do I get from exponential form now to log form now that I have the the base to an exponent on its own side, I can switch it. So I'm going to have log base 3 of x minus 2 equals y minus 1. And then I'll add the 1, and I'll have log base 3 of x minus 2 plus 1 equals y. So our inverse is going to be right there. Beautiful. Okay. So when we're graphing logs, it's helpful to use some smart points, as you see here in that green box, where it says log base b of 1 equals 0, and log base b of b equals 1. So what are we saying there? Well, if we look at the exponential form, we know that b to the 0 is equal to 1, and b to the first is equal to b. So if we can get this right here to equal 1, and also to equal the base, we'll be in good shape. So I can plug in 3 for x, 3 minus 2 is 1, and have this first result. And I could plug in 5 for x to get 3, which would be the same as the base, which would be that second result. So let's see what we've got there. When I plug in 3, I have log base 3 of 1, and I know that log base 3 of 1 equals 0, plus 1 is 1. And then when I plug in 5, I'd have log base 3 of 3, which is just 1, plus 1 is 2. All right, so we have 3, 1, and 5, 2. 3, 1, and 5, 2. Ooh, look at that. That's flip-flopped with these ones, right? That makes sense, right? Because our inverse flip-flop points. X and Y switch. Okay, so I said I had 3, 1, 3, 1, and then I had 5, 2, which is right here. I'm going to plot a few more here by just flipping my X and Y's from this table right here. And there we have it, folks. So these were the two right here and here that I found by doing those smart points, right? You might want to jot that green box down, pause it if you need to. That is very helpful when graphing logs, get those 2 points. And then I went ahead and switched my X's and Y's from this table here. Cool. What about our asymptote? I'm going to grab a lighter reddish color here. We'll go with this pink color. And now I'm going to have a vertical asymptote of x equals 2. Pop that right there. And remember, that graph never touches that asymptote. It just gets infinitely closer to it. Wonderful. What are my domain and range? I'm going to do that next to these in this same red color here, so remember that it's for the inverse. So what's my domain, range, and asymptote? Well, my domain is going to be where it's larger than 2, so from 2 to infinity. My range is going to be negative infinity, positive infinity, so all real numbers are negative infinity to positive infinity. And then my asymptote is now just an x equals 2. It's a vertical line. Look at that. It's nice and easy. You can see the flip-flopping going. Oh, man. Love this stuff. This is fantastic. It's like, well, if I had to do one problem, I want to do 2 problems. And once again, we can even see that these reflect over that y equals x line there, that diagonal line, that parent function of our linear equations. Awesome. Let's keep going. So now in this one, we're given a log function to graph. Right, so we're going to use some of those smart points we were talking about. And then looks like we're going to have to graph the inverse as well on the same graph. So same kind of problem. We're starting with the log function. Now, what are my transformations? Let's jot that down. If it's inside, we're thinking horizontal, so we're moving to the right 3. So right 3. Actually, maybe I'll change colors up here. I'm going to go with green instead. Right 3. Okay, let's think about some points here, some smart points. What would give us 1 inside the log? Well, that would be 4. And then what would give me the same number? That would be 7. So 4 and 7 would be some smart points here. So let's pop those in. If I plug in 4, I get 1 inside the log. I know log base 4 of 1 is 0. And log base 4 of 4 is when I plug 7 and I get 4 inside the log is going to be 1. Nice. All right, so I'm going to go ahead and plot those 2 points. And before I graph these, what do you think could be kind of helpful? We know that we're going to have a vertical asymptote, and since it shifted to the right 3, that vertical asymptote, rather than being x equals 0, will be x equals 3. Perhaps, in a lighter color, I will go ahead and graph that to help me shape my graph here. So I got x equals 3. And now I can start to see my graph take shape. I know the general behavior of a log function is going to follow that asymptote. So I'm going to have something like that. Gets really close to the asymptote, infinitely closer, but never quite touches it. Has that nice curved aspect to it. Beautiful. And from here, I can clearly see my domain and my range. My domain is going to be when it's larger than 3, so 3 to infinity. And then my range is all real numbers, or negative infinity to positive infinity. Nice. All right. So I've got my log graphed. Now on to question 4 here, which is pretty much part of this. Let's find the inverse, and then we're going to graph it on the same axis. I'm going to go with orange here. That sounds fun. So first step, we would change this to a y, and then I'm going to go ahead and switch my x and y. So I'll have x equals log base 4 of y minus 3. Now I'm going to change this, since there's nothing added or subtracted out here. I can go right to changing this to my exponential form. So I'd have 4 raised to the x is equal to what's inside the log, y minus 3. We did the loop backwards again. A lot of times you'll see it written that way if you're a loop and swoop fan. All right, then I just need to add the 3 to the other side. So I'm going to get 4 to the x plus 3. I really add 3 to both sides, but it cancels on the right. So now I have g inverse of x is equal to 4 to the x plus 3. And if I were to pick 0 for my x, I'd get 4 to the 0, which is 1, plus 3 is 4. So I'd have the ordered pair of 0, 4. And then if I were to plug in the 1, I'd get 4 to the first, which is 4, plus 3 is 7. And as you can see, it's the flippy-floppy of those, right? The x and y's have switched. Let's go ahead and plot those 2. And as you can see also, like when I was referencing before, I'm like, hey, it's a little bit easier to plug it into like the exponential. It really is here, right? I mean, I could be like, oh, I'll do 4 to the second is 16, plus 3 is 19. I could do 4 to the negative first, which is 1/4. I'll have 3 1/4. And it's real easy to get those as opposed to when it's in the log form. But 2 points with the asymptote will be enough to graph these. So let's plot 0, 4. And we have 1, 7. And I know my horizontal asymptote, let me get the marker here. I'll go ahead with just like a yellow for this one. My horizontal asymptote would be up 3 rather than to the right 3. There it is. Wonderful. And now I can go ahead and connect these dots, making sure that I don't cross my asymptote. Whoa, my hand kind of moved. Good enough there. All right. I like it. I like it. And as you can see, once again, if I were to throw in with a light blue here, that sounds wonderful. If I were to throw in that 45-degree angle there, that line, that y equals x line, best I can. The graphs aren't always to scale, but I can see that it's going to go ahead and reflect right over that. Whew. Whew. Good stuff. Why don't I toss in my domain and range while we're at it? Well, my domain is going to be from negative infinity all the way to positive infinity. My range, I'm getting as low as almost negative 3, right? It's approaching negative 3. It never gets there, and goes up to infinity. Goes to, did I say negative 3? Hope I didn't. Positive 3. Never quite gets there. And then lastly, my asymptote is y equals 3. Lovely. Couple points. Asymptote. If you know the general shape of the graph, you should be good to go from there. Love it. A little bit more to go. I know this video is getting a little bit lengthy, but I mean, it's exponentially fun when you're graphing logs and exponentials, right? We're logging some fun time here. Can't help myself. So some formal properties here before we do a couple more examples, or I think one or two more examples. If we have our f of x equals log base a of x, where x is greater than 0 and not equal, where a is greater than 0 and a is not equal to 1, our domain is going to be from 0 to infinity, not including 0, right? And our range is going to be negative infinity to positive infinity. We saw that until we started shifting things around. Our x-intercept of the graph is going to be 1, just like our y-intercept for exponentials is 1 until we start shifting, right? There's no y-intercept for a log, much like there's no x-intercept for an exponential until we start shifting around. The y-axis, x equals 0, is our vertical asymptote of the graph, much like our exponential, the horizontal, or our x-axis, is the horizontal asymptote of the exponential graph. Seen those? They're flippy-floppy, right? They're inverses. A log function is decreasing if a is between 0 and 1, and increasing if it's greater than 1, just like our base for our exponential functions. And the graph of f contains the points 1, 0, a1, and 1 over a, comma, negative 1. Remember that we have the a there as our base, right? And smooth, continuous, no corners or gaps, right? We don't have like a V shape, like absolute values, right? It's just a smooth, continuous, wonderfully fantastic graph. All righty. Feel free to pause it and write down if you need to. Otherwise, I'm going to move on. All right, we've seen this e before, yes. Well, with our calculator, let's graph y equals e to the x. And I've done that here on my fancy emulator. As we see here, that one's highlighted right now. We're going to use the other one in a little bit. But I have e to the x. If I graph it, there we are. Where is that crossing? Well, I'm going to zoom in a little bit. Where should it cross based on what we know about exponentials? It should cross, there we go, at 0, 1. So let's go ahead and graph this on our notes here on our xy coordinate plane. I'll go ahead and do that. I'm going to pick, let's see, how about, let's go with, I'm going to go purple again. Okay, so I'd be here at positive 1, and I could plug in some other values, but I think what I'll do for now is I'm going to throw down the asymptote, the horizontal asymptote. I know what it's going to be there. There we are. And I know my graph is going to be looking something like this. Whoa, really bouncing all over the place there. It was a little better. Once you get moving on this thing, then it's all smooth sailing. But it's that start where I'm like a little bit slow to it, right? Okay. So let's get to this next part. E is defined as the limit as n approaches infinity, meaning as n gets infinitely larger, of the quantity 1 plus 1 over n raised to the n. Well, what does this mean? Perhaps maybe we could take a look at a t-chart with some values. As you see here, we've picked 10, 100, 1,000, so on and so forth. N is getting infinitely larger, okay? So I'm going to pull my calculator here, and as you saw, I had something else typed in here. There we go. I'm going to clear this out, and then what I'm going to do is, if you haven't plugged this in yet, why don't you go ahead and do so, pause the video. I'm going to go to my table set, and I've already done it, but if you go over here to go ask, hit enter on that. So it's going to ask us what we want to see. And now I'll go to my table, and I've already tested it's 10, right? So I've got 2.5937, and if I do 100, I get 2.7048. If I do 1,000, and then 10,000, 100,000, so on and so forth. What number is that approaching? If I keep on, they don't have enough room over here anymore, but we're approaching the same number, 2.7183, and it goes on forever. We're eventually approaching the same number over and over. That's interesting, isn't it? So we keep on getting closer to that 2.7183. 7183. And I'm going to pop this calculator back up here and check this out. Ready? Second, quit. If I do e to the first, anything to the first power is itself, right? 2 to the first is 2, 3 to the first is 3, 4 to the first is 4. Mic drop. 2.718. That 2 would have rounded up to a 3. We just didn't see it next. 2, 8, 1, blah, 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 right? Crazy. That was cool. Wasn't that cool? That was super cool. All right, so it keeps getting close to that number. E is that number that it keeps getting closer to. We just showed that in the table. That's fascinating stuff to me. I don't know if you're just like, what just happened? You're probably feeling that way. I just can't tell because it's a video. But I bet you are feeling that way because I know I am. All right? All righty. Let's keep going. The inverse of y equals e to the x. Well, let's go ahead and find that. In order to do so, I got to calm down from that excitement, you guys. I'll use orange here. I'm going to start with x equals e to the y. And when I rewrite this, I'd have log base e of x equals y. And we know that log base e is natural log, right? We said that earlier. So y inverse is equal to the natural log of x. Lovely. Well, why don't we go ahead and sketch this on the same graph? And I know that my log functions are always going to have the point 1, 0, unless we start shifting, right? And I will have an asymptote, vertical asymptote. And let me get I'll go with the yellow again, since I paired it with that last time. Wonderful. Pop some arrows. And now I'm ready to go with this orange one here. Nice. And as you can see, it would reflect nicely over that y equals x line there. This is some good stuff. Cool. So we know the inverse of y equals e to the x, or e to the x is natural log of x. We graph them. We saw a little intro to some limits there. I didn't fill this all in, but we saw it on the calculator table, right? You could fill those numbers in as well. That was, I mean, for me, that was the peak. That was the peak of this lesson right there for me. I mean, that was quite exciting. All right, little mo. Last one here. Last one, I promise. I know this is getting to be a little long here. I'm gonna go green. Finish with the money color. We've got h of x equals natural log of x plus 2. All right, so we have a horizontal shift. That looks like horizontal stretch. So I'm just going to say shift left 2. All right, I like it. So that means our vertical asymptote will be x equals negative 2. Awesome. I like that. And then why don't we pick out some points here? So if we remember our smart points, I want to get the inside there to be 1. So what x value would do that? If I plugged in negative 1 for x, I'd get 1 in there, which would yield 0, an output of 0 for y. So negative 1, 0. And it's a little bit tricky to get this to equal e. Ooh, that was a voice crack. I'm going to leave it. But we could plug in another point if we'd like. I'm going to go with my vertical asymptote here. Some of these are, when the base is e, it's a little bit tricky to get it to equal the base, you know. So I think we'll go with this 1 point here. Pop some arrows on my asymptote. Beautiful, wonderful. I could plug in 0. Let's just do it with the calculator real quick. If I plugged in 0, I'd get natural log of 2, which is going to be 0.693. So close to 3/4. Right, 0.75 is 3/4. So I'm going to be right around up here. Gives me an idea of what's going on. And there we have it. Again, kind of tricky when the base is e to get your what's inside the log to equal that. So a little bit of calculator action there on that one. I think it'd be useful. My domain would be from negative 2, got a little too squiggly there, to infinity. And then my range would be from negative infinity to positive infinity. We talked about the shifting. I think that's all good to go right there. Good stuff. Fantastic. Thank you guys for sticking around. I know it was a lengthy video. America, freedom, rock and roll, Costco. Riverdog Jenny on the gram if you don't follow her yet. I'm sure you do. You should probably follow her. Riverdog Jenny on the gram. It's the best gram ever. Have a wonderful day.